I'll also try recording it. I'm recording it anyways.
Okay, ma'am.
Okay, so in the last class, we had arrived at the equation of motion, or rather the differential equation for my ballistic galvanometer, right? Let's go back to that differential equation. So the differential equation that we had in the last class read something like this. Right. So in the last class, we had stopped at this point. We had this differential equation and we had defined our P, Q and F in this way. So you can see F is nothing but your driving force, and this differential equation is nothing but an equation for a driven harmonic oscillator. And you know what is going to be the general solution for this driven harmonic oscillator? It is not difficult. If you look at this equation, the solution to this differential equation will have two parts. One will be the solution to the homogeneous differential equation, that is you put f equal to 0, and second will be the particular integral. Now since f is a constant force here, it's not difficult to see that the solution to this differential equation will be of the type you've all seen this solution. So you have the homogeneous part and the particular integral f by q square, where m is under root p square minus q square. You must have seen this solution as e to the power minus gamma t by 2, a e to the power m t plus b e to the power minus mt. So you can see instead of gamma by 2, I have p. That's because I have initially defined, you used to call this as gamma and you used to call this as omega naught square. So if you just compare it with what you used to call this, you will see that you would have got e to the power minus gamma t by 2. I would request people to join in from next time if this thing has to be done. That is, I have to keep adding people to join well in time, right? Because every time when somebody joins, I have to click and add that person to the class, right? And my attention gets diverted. It is very difficult for me to do it. So I would insist that people should join well in time from next time. Okay, so we're going to work with this solution. We know that we can characterize or we can divide this solution into three categories depending upon the nature of m, right? So first is when your p square, suppose, oh, before doing that, there is one more thing that you can see from this solution. Now, we've every time discussed that there is always an inherent time scale in a problem. Right? Now, if you look at, compare this solution with your driven oscillator solution, this is also what you call as the transient part, and this is also what you call as the steady state solution. Right? Now, the transient part of the solution has an inherent time scale after which it dies out, and that's why you call it as transient part. and then the system eventually falls into steady state. Now, what is this time scale here that characterizes your transient phenomena? It is this time scale. So let's say P minus T, where this term becomes 1 by E is Pt equal to, so when you can define Pt equal to 1, so you have a T which is of the order of 1 by P. So this is your inherent time scale. That is, if you look at this system so this is the damping time scale. This is the damping term. After a time larger than 1 by P, this term will, because of this exponential sitting here, irrespective of whatever is happening here, irrespective of whatever is the nature of M, after a long time T, what do you mean by long time T? After a time T much greater than this characteristic time 1 by P, your system, your solution, theta T, will simply become F by Q square, right? And this is the steady state solution. So what you see is that if you look at this system, whatever be the degree of damping of that system, if you look at this system for after a very long time T, it would have eventually gone into steady state. And what is the steady state of this system? F here is a constant driving force. Why? Look at the expression for F. The expression for F, or rather F by Q square. What is the expression for F by Q square? Is GE over R plus RG into K, and this is K by C. So K and K gets cancelled. It is G R plus RG into C times E. So it's a constant driving force because you are using a DC source here. So eventually it is going to reach a steady deflection depending upon what is the voltage applied to your ballistic galvanometer. So this is what you understand by steady state solution. If it doesn't click you immediately what I am talking about, you can compare it with when we were doing LCR circuit. In your LCR circuit, what kind of a driving force you had? You had a sinusoidal driving force, right? A voltage which was of the kind sinusoidal. And when you say that in an LCR circuit, the steady state would mean that your charge or your current eventually follows your external driving force or becomes sinusoidal in nature, right? So now here your external driving force is a constant voltage. So your steady state would mean here, that you get a steady deflection, theta t. And what is the magnitude of that steady deflection? The magnitude of that steady deflection is going to depend upon all these quantities, right? So you will have G, which is going to be characteristic of your galvanometer, R, the resistance, and Rg, the external resistance. Rg is the resistance of your galvanometer, right? So the idea is that after a long time T, your solution becomes just F by Q square. That is one thing that I wanted you to note here. Now, again, so depending upon degree of damping in your circuit, you can characterize this solution into three categories. If your solution is such that you have P squared less than Q square, your solution will turn out to be that for an underdamped case. Why? So if you look at P square less than Q square, P square less than Q square means that your M is imaginary and you have sinusoidal solutions here. This condition is what is known as underdamped. So what is going to happen? Your theta t is going to have a sinusoidal behavior and your theta t is going to have a sinusoidal behavior plus this constant driving force. Now, second case is when your P square is greater than Q square. Then your M is real, and that case is what is known as overdamped. That is, this term is eventually going to, so this becomes real solutions. These are real terms, and your solution is an overdamped solution. Third case is when P square becomes comparable to Q square. Then this condition is what is known as critically damped. We are actually interested in this. So let's for some time look at this condition. What does P square equal to Q square mean to me? P square equal to Q square means, so let's substitute for P square. P square is A plus G. So we've got an expression for this. R plus RG over 2K square is equal to K by. You know, people are joining in this late. It is very difficult for me to keep adding people in between the class. From next time onwards, if this has to be done, I am not going to add anybody after 11:35, 11:38. I'm going to stop adding people after that, right? Because it is really very difficult for me to do that. Okay, so P square is equal to Q square gives me A plus G square by R plus RG equal to this. I can reduce this equation. Just do some mathematical manipulation, nothing else. And you can write this as A plus G R plus RG whole square as, sorry, this is not K by I, this is C by K. I'm so sorry. C by K. So this gives you CK by 4, which ultimately gives me G square by CK by 4 minus A square equal to R. So you realize that if you look at the condition for critical damping, quantities on your left hand side are completely characteristics of your ballistic galvanometer. But quantities on your right hand side consist of an external resistance and the resistance of your galvanometer. What does this mean? This means, so in other words, basically, if I want to, so now you reverse this calculation. If I choose my external resistance R in such a way, and I don't know what will that be, I have to figure that out by doing an experiment because I don't know what these quantities are actually. So I cannot do a by hand number calculation and arrive at a value of R. But by hit and trial, I keep changing this R. There will be some point where my R plus RG will balance this quantity on the left hand side, which is characteristic of my ballistic galvanometer, and will give me condition for critical damping. This is what you do when you do rough CDR. You realize that the value of rough CDR is a characteristic of a ballistic galvanometer. People who are working on different ballistic galvanometers, they get different values of critical damping resistance. Rough CDR, first thing. Second thing, you You cannot do a calculation for rough CDR. You have to somehow experimentally do this balancing. And this is what you do in your first part of determining the rough CDR for your ballistic galvanometer, is that you play around with the value of that series R in your circuit. You keep changing it till you see that your ballistic galvanometer goes into critical damping. That is when this condition will be satisfied.
Ma'am,
Yes?
ma'am, in that expression G square by root over CK by 4, the root over is only over CK by 4.
Sorry? G square upon?
Ma'am, root over, ma'am, the root over is only upon CK by 4.
The root is over, yeah. Oh, yeah. The root here. Under root is only CK over 4. Then you do minus A square.
Ma'am, it's over 4 or multiplied by 4?
मेरा तो over 4 आया है भाई. I don't know. यहाँ A square. मेरा तो over 4 आ रहा है. चेक कर ले. फोर के स्क्वायर चेक कर सकते हैं. हो सकता है इंटू 4 आ रहा हो. कोई बात नहीं, जो भी आ रहा है. लेट्स कीप इट व्हाटएवर इट इज. इट डजंट मैटर. वी कैन चेक दिस 4 लेटर. It won't matter to us. Anyways, यहाँ whatever it is, wherever it is, it's just a constant that depends upon my ballistic galvanometer. I will check it. Right? I will check it. It looks like कि ऊपर ही आएगा. Because when I take this in the numerator, I get a 4. I'll get a 4k here. 4k square in the numerator. Four CK. Okay. I think I can cross check it once more. Let's keep it for the time being. Okay. So what I was talking about was determining this, was satisfying this condition by doing a rough estimate. Okay. But now if you look at this condition, you can see that you cannot do much in an experiment by trying to satisfy the condition for rough CDR. You can only make a rough estimate because there is a quantity on the left hand side which you cannot determine experimentally, right? You can only try to achieve this condition by varying the value of R. So by looking at the condition for critical damping, I cannot determine actual value of critical damping resistance from my circuit, right? So then I resort to some other method of determining critical damping resistance, exact value of critical damping resistance in terms of quantities which I can experimentally measure. And you realize that that condition requires you to go into underdamping. Now, at this point, I would like to tell you that when you do the experiment, you are asked to not keep the key in. Why? Because if you go back and you look at the solution, if I keep the key in, I will definitely be able to achieve at some point this condition and I will get a steady deflection, right? I don't want that. So when I do the experiment, I always tell students to be careful about one thing. And that thing is that you just put, so my circuit, let me redraw the circuit, because if you don't see the circuit, you don't understand what I'm talking about. So if you keep this key plugged in, your circuit is a driven oscillator. And a driven oscillator will eventually, after some time t, go into steady state. Now, I don't want my system to go into steady state. Why? Because I want to exploit this part of my solution. So what do I do? What I do is I plug this key in and then I remove it out. And if I do that, then I am able to achieve a solution of the kind this for my underdamped oscillator. So now my oscillator, my harmonic oscillator, is no more a driven harmonic oscillator, but is just an underdamped harmonic oscillator. But I need to plug that key in so as to give it an initial kick, right? Now when I go to underdamped condition and I look at the solution for underdamped condition carefully, now condition for underdamped was that you get M to be imaginary, and you can always write your theta t to be something of the kind, let's say, this is your real part of M. So you will have a solution like this. This solution in the limit M being imaginary can always be written down like this. Right? You can see that this solution has a time period which is equal to and this is not equal to your free oscillation time period. But what was your free oscillation time period? If you remember, your free oscillation time period, we had an expression for free oscillation time period, and that expression for free oscillation time period was t equal to 2 pi k by c. Right? You can see that this will reduce to this if q square is much larger than p square. What is your q square? Q square is your omega naught square, and p square is actually what you have seen as related to your gamma, right, is much greater than gamma square. So if your damping is very weak, your oscillator reduces to a free harmonic oscillator, and your time period, this time period t here reduces to your pre-oscillation time, right? But here you must note that this time period is not equal to your pre-oscillation time. But if I take ratio of two consecutive thetas, theta 1 and theta 2. What is theta 1? Theta 1 is the deflection. So if I look at my scale, first time it goes on this side, let's say I call it theta 1. Second time it goes on this side and I call this as theta 2. So basically, theta 1 and theta 2 are what thetas? So if theta 1 is measured at time t equal to, let's say, 0, theta 2 is something which is measured at time t by 2. Why? Because one full oscillation will be when it comes back to right hand side. So if I take the ratio of theta 1 to theta 2 here, right? If I take the ratio of theta 1 to theta 2 on the right hand side, this ratio is equal to, let me write it. Let's call this ratio as some D. What does it measure? It measures by how much your so you see consecutive thetas are going to decrease exponentially. So this is basically a measure of how much does my theta 2 decrease exponentially with respect to my theta 1. So we call it as decrement. So this EPT by 2 is what I call as decrement, or if I take the log of both the sides, this quantity is what I call as the logarithmic decrement. That is a measure of how much does consecutive thetas decrease is what I call as the logarithmic decrement. Right? Now, why am I doing all this? Why am I working with this? This is because you look at the left hand side. It goes as PT by 2. You realize that PT by 2 contains characteristic constants of your galvanometer. Lambda, on the other hand, on the right hand side, is something that I can determine experimentally. Why? Because the way I have defined it, it's the ratio of theta 1 to theta 2. Theta 1 and theta 2 are quantities that I can observe experimentally. So lambda is a quantity that I can actually measure experimentally. On the left hand side, I have something which is a characteristic of my galvanometer. Now, if you go back and you look at the equation for R plus Rg that we just had some time back, again, R plus Rg is something that I can control experimentally. But it depended upon something which was characteristic of my galvanometer. So my idea is that the quantity that I had on the right hand side of my Rg, which was basically G square over 4k, I don't remember, 4ki minus a square, is that somehow I am able to relate this to this. And then I'll be able to experimentally determine this R in terms of the logarithmic decrement and not do a rough estimate by balancing something, right? So that is the aim. So now what I'm going to do is that I'm going to find a relationship between something like lambda and a quantity here, right? So let's go back to this equation. Now what do I have? What I have is something like this. What I have is that 2 or rather PT by 2 is my lambda. Sorry, log of lambda. Log of D, or I can write T as 2 lambda or this can also be written as, or this T is equal to, so what do I have? I have lambda by Q square. Substitute for Q square and P square. First to take this P here. Or I can also do something like this. I've just substituted for T naught. Combined all these expressions and substituted for T naught. I can do some more mathematical manipulation and write this in a slightly different way. I want to do and I have what I wanted. Look at this and look at this quantity here. So I have indeed got a relation after doing mathematical manipulation. A relationship between R and lambda. I call this quantity as some function of lambda, f lambda, and rewrite this equation. Now this function has few interesting properties. Is that if I look at the value of this function for r equal to infinity, this r equal to infinity, I call the corresponding value of lambda as lambda infinity. Value of this function for r equal to infinity is what? This term is 0. So it is just T naught by 4k . So I can rewrite this equation here as but if I look at this expression for f lambda and substitute here, look at what happens to this function, that is find the value of f lambda infinity. What does r equal to infinity mean? If you look at the condition for logarithmic decrement, you realize that as R becomes larger and larger, the degree of damping in your circuit decreases. That's because the current in your circuit decreases, and as a result, all the damping terms